Greetings, Dr. Dan with Optimal Optics here to introduce Unit 15, Lens Aberrations. Some people might say that geometric optics is an aberration. I disagree. So we'll start with spherical aberration. I've drawn a convex lens, the optical axis, and the lens's center at C. Now we know if we send in a ray along the optical axis, it is undeviated. If we send in a ray close to the optical axis, this blue ray, let's say it is focused where the blue ray meets the optical axis. I've drawn the normal through the center, and remember that the angle of incidence is the angle between the incident ray and the normal. Now we'll send in a ray that's further from the optical axis and also further from the optical center. And if we draw our normal, we see that the angle of incidence is larger for this ray that's further from the optical center. And therefore, the angle of refraction will also be larger, and its refracted ray, will be focused closer to the lens than the ray that was close to the optical axis. That is spherical aberration. As you get further away from the optical center of a lens, as the incident ray gets further away from the optical center of a lens, the spherical aberration increases. If the blue ray was 1 centimeter from the optical center and it had a certain amount of spherical aberration, and if the red ray was 2 centimeters from the optical center, its spherical aberration would be 4 times the aberration of the blue ray. To take care of that, lens manufacturers make what are called corrective curve lenses. And a corrective curve lens has flatter edges, and therefore they do not refract the light as much as they otherwise would. And it decreases the spherical aberration of the lens. So if we had, let's say, this convex lens, a corrective curve lens would flatten out the periphery. Another lens aberration is astigmatism. We learned in Unit 11 about astigmatic or cylindrical lenses. You could take a spherical lens and make it a spherocylinder lens simply by tilting it. So here we have our black optical axis with the center of our convex blue lens, the vertical line at C, and we're sending in a ray, the blue line, the blue horizontal line, and let's say it's focused over there after being refracted. Now we're going to tilt our lens. So the axis, the point at which it's being tilted, is where all the lines intersect. So this axis or axle goes through the screen and toward your eyes. And now you can see that that same ray has a greater angle of incidence, and therefore it's going to have a greater angle of refraction, and it will be focused closer to the lens. And all of the rays along that meridian will be focused closer to the lens. So effectively, the sphere lens has become a spherocylinder lens simply by tilting it. And there's the angle of incidence, and there's the angle of incidence. So there's a formula you can use to actually calculate what the new sphere power is, the new cylinder power is of this tilted lens. So the new sphere power is equal to the power of that spherical lens plus times 1 plus sine squared theta over 2n, where theta is the tilt and n is the index of the lens. The new cylinder power equals that new sphere power that we just calculated times the tangent squared of theta. Talk now about chromatic aberration, first in prisms. The concepts of chromatic aberration in prisms and lenses are the same, and the formulas are very similar. So when we send white light into a prism, out come the colors of the spectrum, from red to blue. The reason that they are bent differently is because red has the longest wavelength, if you recall unit 1 on the electromagnetic spectrum, and therefore it interacts less with the material of the prism than the blue light, which has the shortest wavelength and interacts more with the material of the prism and therefore is bent more, refracted more. If you recall unit 6 on prisms, the deviation of a prism equals n minus 1 times beta, the refracting angle of the prism. And to calculate the deviation of these different colors, you substitute the index of refraction of the prism for red, for blue, and for yellow. The letters that designate those colors are C for red, F for blue, and D for yellow. Now you might ask, why don't we use R for red and B for blue and Y for yellow? And you can blame that on Joseph von Fraunhofer, a German physicist who lived in the late 1700s and early 1800s. And he found, when he examined the spectra of light from stars and from the sun, there were distinctive black lines in certain colors. These dark lines are areas where elements in the star or sun absorbed certain selected wavelengths of light. The colors where these black lines were formed, he assigned letters to them. And as you can see, red is C, yellow is D, and blue is F. So I've shown the deviation of the red light, yellow light, and blue light with those red, yellow, and blue arcs above. This is omega, another Greek letter, and that is what we call dispersion. And it's the degree to which the wavelengths of light are spread out. And of course, there's a formula for it. And omega equals n sub f minus n sub c over n sub d minus 1. V is called the reciprocal relative dispersion. Reciprocal means we flip the fraction. V is also called the Abbe number, named after Ernst Abbe, another German physicist who lived in the late 1800s and early 1900s. So V equals n sub d minus 1 over n sub f minus n sub c. That's the reciprocal. And the first two letters of Abbe are the first two letters of aberration. He was destined to write this formula. A larger Abbe number means that there's lower dispersion or less chromatic aberration for that material. If you think about the denominator, n sub f minus n sub c, if that's a smaller number, if the spread is less, you have a larger Abbe number. Chromatic aberration equals P over V, where P is the prism power for yellow light. If there's no little letter in the lower right, no subscript, you can assume that the variable is for yellow light. Now, we can create an achromatic prism. Achromatic means that there's no chromatic aberration. And we do that by placing two prisms of different materials, and therefore different Abbe numbers, where their bases located opposite each other. The formula for calculating those prism powers are P, which is the total power of the combined prism, equals P1, which is the power of the first prism, yellow light, times, in parentheses, V1 minus V2 over V1, where V1 is the Abbe number of the first prism, and V2 is the Abbe number of the second prism. By the way, if you want to get more information about this topic, you should ask a rainbow, because rainbows always pass their tests with flying colors. Also, if you're interested in knowing what's at the end of a rainbow, it's the letter W. So the formulas for chromatic aberration for lenses are very similar to the formulas for chromatic aberration for prisms. So the formula for chromatic aberration in a lens equals NF minus NC times the power of the lens in yellow light. To reinforce that, I'll put a little d there, but it's not necessary, over n sub d minus 1. It's the same thing as the power of the lens over its Abbe number. To construct an achromatic lens, we take two lenses of different materials and different Abbe numbers and glue them together. And the formula for the total achromatic lens, F, equals the power of the first lens, F sub 1, times, in parentheses, V1 minus V2 over V1, where V1 is the Abbe number of the first lens and V2 is the Abbe number of the second.